Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand intellectual theatre of the early 20th century, few figures occupied a position of such magisterial authority as David Hilbert. From his throne in Göttingen, the undisputed world capital of mathematics, he surveyed the landscape of knowledge with an architect's eye, seeking to replace the rickety, intuition-laden structures of the past with magnificent edifices of pure, logical form. His grand project, articulated most famously in his 1900 Paris address, was the complete axiomatization of all mathematics, a quest for certainty and coherence in the foundations of thought. While this program is often associated with pure mathematics, its most audacious and physically consequential expression arrived in 1915. In his paper, Die Grundlagen der Physik, or The Foundations of Physics, Hilbert extended the reach of his axiomatic method from the abstract realm of geometry to the very fabric of spacetime, deriving the field equations of general relativity from a single, elegant mathematical principle. This endeavor represented a pivotal moment, an attempt to demonstrate that the fundamental laws of the universe could be deduced from axioms of mathematical beauty, a profound statement on the relationship between formal systems and physical reality. The genesis of Hilbert's 1915 work lies in his earlier, triumphant axiomatization of geometry. His 1899 monograph, Grundlagen der Geometrie, had systematically rebuilt Euclidean geometry from the ground up. He established a set of 20 axioms, meticulously organized and proven to be consistent and independent. This work did for Euclid what a modern engineer does for an ancient blueprint. It preserved the essential structure, while replacing ambiguous assumptions with rigorously defined components. The philosophical underpinning was radical. For Hilbert, the objects of geometry, the points, lines, and planes, required no intuitive meaning. They could be tables, chairs, and beer mugs, so long as they satisfied the formal relationships prescribed by the axioms. Mathematics became a game of symbols, and a proof was a demonstration that a particular configuration of symbols followed from the initial rules. This formalist philosophy, which sought to secure the foundations of mathematics by draining its concepts of all semantic content, was the weapon Hilbert would bring to bear on the problems of physics. The intellectual environment of Göttingen, a crucible of innovation, where the pure mathematics of Bernhard Riemann had already laid the groundwork for curved spaces, provided the perfect setting for this ambitious leap. The stage was set for axiomatization's greatest challenge, the cosmos itself. The year 1915 found the world of theoretical physics in a state of intense, creative ferment. Albert Einstein, having laboured for years, was on the verge of completing his theory of general relativity, a revolutionary conception of gravity as the curvature of spacetime. He was, however, grappling with the final, precise mathematical formulation of his field equations, particularly the challenge of achieving general covariance, the principle that the laws of physics must take the same form for all observers. In the summer of that year, Einstein visited Göttingen and delivered a series of lectures on the state of his theory. Hilbert, a supreme master of the mathematical techniques Einstein was struggling with, listened with profound interest. He saw in Einstein's physical principles a problem ripe for his axiomatic method. Where Einstein wrestled with thought experiments involving accelerating elevators and bending light rays, Hilbert perceived a challenge of pure mathematical construction. The task, as he saw it, was to identify a single, overarching world function, or what we now call an action principle, from which all the fundamental laws of physics would emerge as a logical consequence. This represented a profound divergence in approach. Einstein sought a theory that described the world. Hilbert sought an axiom that generated a whirl. The result of Hilbert's focused effort was a breathtaking display of mathematical power. In his paper, submitted to the Göttingen Academy on November 20, 1915, he proposed a single, startlingly simple action principle. The core of his formulation was an integral taken over a four-dimensional spacetime continuum, the quantity being integrated, the Lagrangian density, had to be a scalar invariant, a quantity that remains unchanged under arbitrary coordinate transformations, thereby guaranteeing the general covariance that had so troubled Einstein. Hilbert proposed the simplest and most natural candidate available from the language of Riemannian geometry, the Ricci scalar curvature, a measure of spacetime's intrinsic curvature, which is often denoted by the letter R. By applying the principle of least action, a well-established tool from classical mechanics, to this Hilbert action, The field equations of gravity emerged with a feeling of mathematical inevitability. These equations, a system of 10 coupled, non-linear partial differential equations, is a direct relationship between the geometry of spacetime, encoded in the metric tensor, and the distribution of energy and momentum within it, encoded in the stress energy. In their modern compact form, they state that the Einstein tensor, G sub mu nu, is proportional to the stress energy tensor, T sub mu nu. Hilbert had, through an act of pure mathematical reasoning from a single axiomatic principle, derived the laws governing the cosmos. He had axiomatized gravity. This near-simultaneous discovery of the final form of the field equations ignited one of science's most discussed priority, disputes. Hilbert's manuscript was submitted 5 days before Einstein presented his final, correct equations to the Prussian Academy of Sciences. A simplistic reading of the dates would award Hilbert priority. The historical reality, as revealed by later analysis of Hilbert's original proofs and subsequent publications, is far more nuanced. Hilbert's first version of the paper may have lacked the explicit form of the equations, and his later published version graciously acknowledged Einstein's foundational contributions. The true significance of this episode lies beyond a mere squabble over precedents. It offers a luminous case study in the divergent methodologies of scientific genius. Einstein's path was one of relentless physical intuition, a decade-long odyssey guided by principles drawn from observation and deep philosophical conviction, such as the principle of equivalence. He reached the summit by climbing the rugged, winding mountain trail. Hilbert, by contrast, was hoisted to the peak by the elegant machinery of pure mathematics. His solution was a testament to the idea that the universe's structure is a reflection of mathematical elegance. The debate itself illuminates a central tension in theoretical physics: the relationship between physical insight and formal consistency. Was Einstein's physical reasoning the essential element, or was Hilbert's mathematical framework the true discovery? The question remains a subject of sophisticated debate. The legacy of Hilbert's 1915 paper and the axiomatic method it championed is monumental, its influence rippling through the subsequent century of theoretical physics. The very environment Hilbert fostered in Göttingen became a wellspring of modern physics. To resolve a conundrum regarding energy conservation in his own theory, Hilbert invited Noether, a brilliant mathematician barred from a formal faculty position due to her gender. Her resulting work in 1918 yielded Noether's theorem, a profound statement, linking every continuous symmetry in a physical system to a corresponding conserved quantity. This theorem is a foundational pillar of the standard model of particle physics and quantum field theory. Another of Hilbert's colleagues, Hermann Weyl, took the axiomatic program even further, attempting to unify gravity and electromagnetism by generalizing the geometric structure of spacetime, a direct intellectual extension of Hilbert's 1915 paper and a forerunner of modern gauge theories. More broadly, Hilbert's action-based formulation became the dominant paradigm. The Lagrangian and Hamiltonian approaches, elevated by Hilbert from a useful tool to a foundational principle, are the bedrock upon which quantum field theory, string theory, and essentially all of fundamental modern physics are built. Physics today is largely done in the language Hilbert perfected. In conclusion, David Hilbert's 1915 application of the axiomatic method to the foundations of physics stands as an intellectual landmark of profound and dual significance. It was the ultimate expression of his formalist vision, a demonstration that the intricate dance of planets and light across the cosmos could be derived from an axiom of spare mathematical beauty. This achievement bestowed upon physics a new standard of logical rigor and structural coherence, solidifying a methodological approach that continues to dominate theoretical inquiry. It affirmed the Pythagorean dream that the laws of nature are written in the language of mathematics simultaneously. The episode serves as a powerful cautionary tale. It highlights the tension between mathematical formalism and physical intuition, a concern that Einstein himself would harbour about later developments in physics that seemed to lose contact with empirical phenomena. Hilbert's work, born from a desire for absolute certainty and logical purity, paradoxically opened the door to theories of such abstraction that their connection to the observable world can seem tenuous. The foundations of physics is thus a monument to the astonishing power of pure thought to unlock the secrets of the universe, and a perpetual reminder of the delicate, essential dialogue between the formal elegance of our models and the messy, contingent reality they seek to describe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.